Okay, having reviewed set theory, we're now ready to build up an axiomatic theory of probability. What axiomatic basically just means starting with some fundamental axioms. So our basic model for probability is going to include the following ingredients. So we're going to start with an experiment, and that is a procedure for generating observable outcomes. And in our minds, we should just keep in mind that this experiment is where the randomness comes from. An outcome of an experiment is just a possible observation. All right, and we're going to use this notation in purple, little omega, to denote abstract outcomes. And the sample space, big omega, is going to be the set of all possible outcomes from this experiment. Okay, we'll do some examples, but those are the definitions we need. An event is just going to be a subset of the sample space. It's going to be a collection or a set of possible outcomes. All right, so these are the basic, this is the basic terminology that we need to get started. To make a quick comparison, so we talked about set theory, now we're talking about probability theory. So the names have changed, but they kind of mean the same thing. Sample space means universal set, outcome is the same as element, and event is the same as set. So they basically mean the same thing, but we use this language in probability to be clear that what we're talking about and within this, domain of probability theory. And overall, this framework is going to be easier for us to understand and appreciate by just working through some examples. So let's just get started with that. Okay, our first example, what we're going to do is we're just going to have an experiment, which is to roll a six-sided die. All right, so we're just going to roll this die once, and we're going to record what we see on the top. Okay, that's it. That's the experiment. The outcome, so we're worried about what outcome do we have? Well, that's just going to be a number, and the number omega can take values 1, 2, 3, 4, 5, and 6. So what's the sample space? That's simple. The sample space is just the set of all possible outcomes, which is 1, 2, 3, 4, 5, 6. That's set. Let's talk about some possible events. There are many possible events. Here are 2. So E1 is going to be that the roll is odd. I've told you this now in words. So this is a rule in words. And a list is going to be 1, 3, 5. So that's kind of putting this into the context of the sample space. Another event, E2, is going to be that the roll is less than 3. Okay, so which outcomes meet this rule? Just the outcomes 1 and 2. All right, so that's a simple example of an experiment. Let's do another one. All right, so let's have example 2. In this example, we're going to still keep with this dice example, but we're going to now say I'm going to roll the same die twice. And just to keep things simple, let's say that this is a 4-sided die and that the order in which we see the rolls matters. Okay, why 4 sides? Just so I don't have to write too much. So the outcomes, it's going to be a pair, and omega is going to be a pair ij, and the ij values are going to be 1, 2, 3, and 4. Those are the kinds of outcomes I can see. So the sample space just consists of all possible outcomes. So there are going to be 16 distinct pairs. And so if I want to write this using set builder notation, I have the pairs ij such that ij take values in 1, 2, 3, and 4. Okay? Or I could just list it. So I could write 1, 1, up to 1, 4, up to 4, 1, up to 4, 4. And maybe we could kind of figure out what's going on. But I think the set builder notation is a bit more clear. Okay, let's write out some possible events. Okay, so let's say event E1 in this case is going to be that the sum of rolls is a 4. Okay, so let's list out the rolls that satisfy that the sum is 4. Well, the first one that comes to mind is 3, 1, 3, and then 2, 2, and then also 3, 1. Okay, so those are the possible rolls that actually add up to 4. Okay. What about the event where the rolls that I see are equal? So let's say E2 is the event that the rolls are equal. Well, that's simple. Those are going to be the pairs 1, 1, 2, 2, 3, 3, and 4, 4. Okay, let's move on. For our last example, we're going to do something that maybe we all have some experience with. So as an experiment, we're going to walk to St. Mary Street, and we're going to go to the subway. So we're going to go to the Green Line station, and we're just going to wait for a train, right? So I'm just going to stand on the platform, wait for an inbound train, and I'm trying to go to Boston, so it's inbound. And what I'm going to do is I'm just going to look at my phone, and I'm going to record the time that I'm waiting for the train to show up. And let's say that the units are going to be minutes. And just to, stick with this example, I'm going to say that I'm including all the decimal points down to the, as many decimal points as it takes to describe this answer precisely. So the outcome is just going to be a non-negative number, a non-negative real number, in fact, omega. All right. And so what's the sample space? So the sample space, big omega, is just going to be the interval starting from 0 going all the way to infinity. All right, that's it. So the positive numbers and then, or non-negative numbers. The possible events I'm interested in, let's say that I want E1 to be that the train arrives in under 2.5 minutes. So I don't have to wait too long for the train. Let's say that that's 2.5 minutes. Okay, how do I write this using a set? I can just write starting from 0 up to 2.5 not inclusive, right? So I don't include 2.5 because I said under 2.5 minutes. Let's look at another event. Let's say it's kind of annoying. I'm standing there for a long time. The train takes more than 20 minutes to arrive. Maybe there was a snowstorm, so I'm just waiting on the platform for a long time. So then I have 20, again, not inclusive because it's more than, all the way up to infinity because maybe, the train is not going to show up ever, which, sounds unusual, but if you've ever waited for the Green Line, it kind of makes sense. All right, so let's talk a little bit more formally about an event space. So this is another concept that we need, and we write with this script E. So this is going to just be a collection of subsets of the sample space, omega, and it's going to satisfy some rules. So it's going to, first of all, contain the sample space as a possible event. It's going to be closed under complements. That means that if A is in the event space, so if some event A is in the event space, then a complement must also be in the event space. And it's also going to be closed under countable unions, meaning that if A1, A2, etc. are in the event space, then their union must also be in the event space. Okay, so these are some rules that I have. They seem kind of arbitrary. They don't have to be chosen exactly this way, but basically any choice kind of works out to be the same thing. And this is a really important thing to have underneath our framework, but it's not important for you at this point to appreciate exactly why. It's just to know that it's there. The main thing is we're only considering events belonging to the event space E. And the reason for this is that we're trying to avoid some mathematical issues that we would have to deal with or we would encounter if instead we took E to be any possible subsets of the sample space, right? So if I said that there are no restrictions, you can construct events using any subsets you'd like of the sample space, some weird things would eventually start to happen. But these things are actually pretty weird. And in fact, if you're looking at a finite sample space, so like let's say a dice roll or anything with a finite number of outcomes, there are no issues. So let the event space be the collection of all possible subsets. There will be nothing that goes wrong. Okay, so this is really when we're thinking about things like real numbers, then we have to be a little bit careful about what events we're actually allowed to consider. And just keep in mind that these event spaces have been kind of pre-constructed and thought about for you so that problems do not arise. Okay, so it's not something you have to build for yourself. It's just something that you should know is there to prevent any possible issues. Okay, so now what we need is a way to assign probabilities to events. All right, and roughly speaking, what we want is that the probability of an event should just reflect how likely it is to see an outcome belonging to that event. Okay, so that's what it actually means. So basically, if I'm talking about an odd dice roll, then I'm thinking about the probability maybe should be half. Sometimes it's useful for us to think about probability as some kind of physical property. Okay, so maybe it's something like mass or temperature. It's some kind of property like from physics. But this is just to develop some back of the envelope intuition. Really, we should remember that probability is a mathematical construct, right? So it's built up from these axioms, and it's not really a property that we're learning from empirical measurements, okay? So if I'm interested in calculating probabilities, what I need are some assumptions, and I need some rules for calculating probabilities, I don't need to just go and roll a dice a bunch of times and count. Okay, so that's how we really think about it from first principles. Okay, so now we're ready to talk about how to assign probabilities. We're going to have the probability axioms. So the probability measure is something that's going to, so it has this P with a line through it. That's the probability measure P. It's going to assign probability values from 0 to 1 to every event in the event space E. Okay, so if an event is in the event space, it will have a probability, and the probabilities that I have will satisfy the following three axioms. First, for any event A in the event space, the probability is non-negative. You cannot have negative probabilities. It's called non-negativity. 2, the probability of the sample space is 1, which means that the probability of seeing something occurring, whatever it is 1. So something will occur. We call this normalization. So I normalize the total probability to 1. And finally, in kind of the most interesting property is that for any countable collection, A1, A2, and so on, of mutually exclusive events, then the probability of their union is the sum of their individual probabilities. So another way of writing the same thing is that I'm trying to take the probability of the union, and I just end up with this summation of probabilities. By the way, this is countable additivity, and we'll usually just call it additivity. So what is a collection that is countable? So what's a countable collection? Well, it just means I can index it by the natural numbers. Okay, and really I'm going to point you to your lecture notes for more details. But here you'll just note that the way that I wrote this collection, A1, A2, and so on, it is indexed by 1, 2, and so on. So it is countable. There's no problem. And you would actually have to try pretty hard to build something that is not a countable collection. So again, don't worry about it. See your notes for details if you're interested. And usually this kind of issue won't come up. It'll just, apply automatically. Okay, so some basic intuition for probabilities. Let's say I have an event and the probability is 0. That's like saying that this event does not occur. If the probability of that event is 1, it means that that event always occurs. And if the probability is between 0 and 1 strictly, it means that the event sometimes occurs. And higher values of the probability, so if PA is larger, it's proportional to a higher likelihood of occurrence. Okay, so the probability helps me determine how likely it is for something to occur. And now I have all of my ingredients, okay? So all the components that I need to build up a probability framework are there. And we're going to be using this as a foundation for everything we develop in the course. And that's the important thing to note, that this is really the foundation, and most of the techniques we're going to be using in solving complex problems are not going to be directly from this foundation, but are going to be built up from it. Okay, so we might use some of the properties from time to time, but some of the other things like the event space and other more intricate details, we won't really see them directly, but we just know they're under the hood. Let's summarize. Okay, so let's summarize and draw some pictures. So let's start out, let's say that we have a probability space. That's a sample space, an event space, and a probability measure. Okay, let's do that in a little bit more detail. So sample space is the set of possible outcomes I can see. I'm going to draw you a little example. Here's a sample space, and it has 3 possible outcomes, A, B, and C. Okay, so that's a visualization of a finite sample space with 3 outcomes. The other thing I need to specify is an event space. So the event space is the set of possible events, each of which has to be a subset of the sample space. Okay, and we just said that we can't have all possible subsets. We have to have some rules, but we're not going to worry about that. And in this case, since it's finite, we really don't have to worry about it. We're going to take all possible subsets. And that's what I'm going to draw now. I'm going to illustrate all possible subsets of 3 things. So here's the event space, and I have B as an event, C as an event, A as an event, A and B as an event, A and C as an event, B and C as an event, and the empty set and the sample space as events. So those are all the possible events I can have. Everything, nothing, individual things, pairs of things. Finally, I have the probability measure. So the probability measure is going to take these events, in this case, all possible subsets. It's going to assign them probabilities between 0 and 1. And so let's draw the interval between 0 and 1, and let me just start assigning probabilities kind of arbitrarily, right? So maybe I have some property I want to satisfy, like maybe I want things to be equally likely. In this case, I'm just kind of assigning them in just some way that satisfies the axioms, and we don't need to worry about exactly what values I've picked, just that the axioms are satisfied. So first, probability of the empty set will be 0, because the probability of nothing occurring is 0. Then the probability of the sample space is 1 because of normalization. So the probability of something occurring is 1. The probability of A, I'm just going to decide is 1/4. Okay? And notice that I wrote A, instead of writing probability of A, I wrote probability of the set containing A. And that's important because it's an event, which is a set, rather than an outcome, which gets the probability. Also going to write the probability of B. I'm going to decide that has probability half. Again, notice that it's the set containing B, which is an event. And I'm going to write the probability of C, which is an event. And probability of A and B is going to, due to countable additivity, be the sum of 1/4 and 1/2, so it has to be 3/4. The probability of A and C is the sum of the probabilities of A and C, so it has to be 1/2. And the probability of B and C is going to be the probability of B plus the probability of C, so 1/4 plus 1/2, so it's 3/4. That's my probability measure, and that's the whole probability space. Let's talk about some basic probability properties. So one is going to seem maybe too simple, but we're going to say it anyway. So let's say I have a finite collection of mutually exclusive events, A1, A2 up to AN. Their union, the probability of the union is the sum of the probabilities. The only difference between this and countable additivity is that instead of taking the union from 1 to infinity, I'm taking it from 1 to n. And that might seem like a very, very subtle distinction, and it is. Okay, so that's it. It's just a very subtle distinction, but I'm just telling you or reminding you that it's okay to take a finite union instead of an infinite union. In fact, you could even use this for just two mutually exclusive events. Let's just call them A and B. So the probability of the union of A and B is the probability of A plus the probability of B. Probability of empty set is 0. We kind of saw that before that. You can derive using the axioms. And for any event A, the probability of its complement is 1 minus the probability of A. This is called the complement property. And for any events A and B, if I want the probability of their union, it's the probability of A plus the probability of B minus the probability of their intersection. This is called the inclusion-exclusion property. Why do I need to do this? Why subtract the probability of the intersection? Why can't I just add things like I was doing above for mutually exclusive events? Well, let's look at a picture. Here's a sample space. Here's A. Here's B. And they overlap. The problem is, when I add up probability of A plus probability of B, I count the intersection of A and B twice. So I add up the probability of the intersection of A and B twice, which is bad. So I have to subtract one of those copies. And that's why I need the inclusion-exclusion property. Okay, let's go back to example 1 and work out some probabilities. Okay, so what was example 1? Maybe we've forgotten. In example 1, we were setting up an experiment where we rolled a 6-sided die. All right. And the sample space in that case, we worked it out to be 1, 2, 3, 4, 5, and 6. Let's assume that since it's just a normal, fair, unweighted die, that the outcomes are equally likely. Okay, so it's the probability of seeing the event containing 1 is equal to the probability that I see the event containing 2 up to the probability that I just see the event containing 6. And that's just alpha. So I just decide that that's called alpha. So I want to solve for this alpha. What should alpha be? Okay, well, first of all, before we do any formal calculations, we can just guess that alpha should be 1/6 because there are 6 possibilities. They're equally likely and they need to add up to 1. And that's basically what we're going to see. Okay, well, let's do this formally. We know that the sum of the probabilities of these events from 1 to 6 is equal to the probability of the sample space by additivity, right? So these are mutually exclusive events that cover the sample space. So by additivity, these are equal. And that has to be 1 by normalization. Okay, so then taking these two facts together, what I find is that the sum of the probabilities of these individual outcomes is just going to be the sum from 1 to 6 of just alpha, because they have the same probability. So it's just that's equal to 1. So that's the same as saying that 6 alpha is equal to 1. And that's the same as saying alpha is equal to 1/6. Okay, so same thing I was saying intuitively, but we did it formally. What is the probability that the roll is odd? If you remember, one of the events that we wrote down, just as a possible event, was the event that the roll is odd. Okay, so I'm asking about this problem in words, and I need to sort of translate this into an event. So remember, we called that the event E1. So what's the probability of E1? It's the probability of seeing 1, 3, or 5. So by additivity, I can decompose this into probability of 1 plus the probability of 3 plus the probability of 5, okay, using the additivity property. So it's just going to be a sixth, right? So each of these components has probably a sixth plus a sixth plus a sixth, and that's going to add up to a half. And again, that meets with our intuition because half the time the roll should be odd, so we expect that the probability should just be 1/2. What about the event, the second event that we saw? So that was the probability that the roll is going to be less than 3. Okay, so let's just think about this intuitively. That's when it's 1 or 2, so that should be a third, but let's work it out formally. So less than a 3 is the probability of this event E2. So that's the probability that I see either 1 or 2 as my outcomes. And so by additivity, I'm going to get the probability of 1 plus the probability of 2, right? So by additivity, I can decompose the union into these mutually exclusive events, 1 and 2. And so then I just add up their probabilities. So it's a sixth plus a sixth, which is a third, which is what I expected. Okay, let's now work out something a little more complicated. So what's the probability that the roll that I see is odd and less than 3? Okay, so I want both things to hold simultaneously. Well, formally, this is like taking the intersection of events. So I have the probability of the intersection of E1 and E2. So the only thing that they share is 1 as an outcome. So that's just going to be a sixth. What if I want to know the probability that either it's odd or less than 3? So that's the union, probability of E1, union E2. So that's the probability of 1, 2, 3, and 5. So those are all the outcomes that I find in E1 or E2. So that's 4/6, which is 2/3. Why is it 4/6? It's just 4 things, and they're all equally likely. So I just wrote 4/6 instead of writing a sixth plus a sixth plus a sixth plus a sixth. Okay, so can I get this in a different way? Alternatively, I actually already did the calculations I need, and I could have used the inclusion-exclusion property. This was a great place to use it. So I could have written this union as the probability of E1 plus the probability of E2 minus the probability of their intersection. And I need to do this because there is overlap. So E1 and E2 are not mutually exclusive. So I have to use this formula, and I get a half plus a third minus a sixth, all of which I've worked out before to get 2/3, which is the same thing I got from working it out directly. In this case, it's simple. I can work it out directly with no issues. But in some cases, these kinds of shortcuts can be very convenient. All right, so one thing I've mentioned before, but just to reemphasize it, if I have a finite number of outcomes in my sample space, it is completely fine to take the event space to just be the possible subsets of the sample space and not worry about it, and then just take the probability measure to be what I get by assigning probabilities directly to outcomes. Okay, so normally I shouldn't do this, but when it's a finite number of outcomes, it's fine and I can not worry about it and proceed. So as an example, let's run the following experiment. Okay, so this is a silly experiment, but it kind of lets us visualize a little bit. So I'm just going to go and ask a stranger which city they prefer to visit. Okay, so let's say I only give them the options of Boston, Chicago, Los Angeles, New York, and finally, let's say San Francisco. So those are the only big cities that I list for them. Ask them which one they would prefer to visit if they want a contest or something like that. Okay, so the sample space of possible outcomes here is just, let's say in red, I write BOS, so for Boston, then I write in blue, Chicago, and then I write in orange, LA, and then in purple, I write New York, and then finally in green, I write San Francisco. Okay, so this is my sample space, and I'm just using colors to distinguish between these cities. Okay, and now I need to assign probabilities to make this all work out. So maybe I should have some principled way of doing this. I'm just going to write down some probabilities. You can just think of this as part of the problem statement. And so the probability of Boston is going to be the highest one because we all like Boston. It's going to be a third. And let's say the probability of Chicago is going to be a sixth. Okay, so probability of Chicago is just 1/6. And probability of LA is going to be an eighth. And remember, I'm always using these curly brackets to denote events. So it's not just the probability of the outcome, but the probability of the event containing a single outcome. And the probability of New York is going to be an eighth. And finally, to get everything to add up to 1, I'm going to take a fourth to be the probability of San Francisco. Okay, so let's see. What's an interesting thing I can ask here? Maybe what I should ask is, how can I visualize this? So first of all, I'm going to just illustrate the cities here and put probabilities as the heights on this plot. So basically, I'm just showing you by drawing different heights the probabilities of preferring each city, just so you can get some kind of visualization of what this probability kind of means. Okay, let's define another event. Let's say that I'm interested in knowing whether someone prefers a West Coast city. So West Coast city, so which cities are on the West Coast here? Well, I only have 2. I have LA and I have San Francisco. Okay, so I have 2 cities on the West Coast. That's my event W. What's the probability that someone answers a West Coast city? So this is basically the probability that their answer consists of one of these 2 cities. So you're aggregating that probability. So this is the probability of LA SF as an event. And so by additivity, I can just decompose this to be the probability of LA plus the probability of SF, right? Those are mutually exclusive. And I already have those probabilities written down as part of the problem statement. So I can just look them up. It's just an eighth plus a fourth. So that's just going to be 3/8. Okay. And we're going to use this example a little bit later, but I think that's it for now. I'm going to close out by talking about one more issue, which is a little bit more intricate. Okay, we just saw what happens when the sample space is finite, but what about other scenarios? So let's say I'm dealing with a scenario where the sample space is uncountably infinite. Okay, so before I get into that, I just want to emphasize that we're going to think about this more as from the perspective as an example and just something to keep in mind. And this is not necessarily something we want you to worry about in terms of doing homework or solving problems. But we just want to kind of show you some of the intricacies hiding inside this framework. Okay, so let's just take an example of an uncountably infinite set, a very simple one. So let's just say the unit interval is the sample space. Okay, so it just turns out that you can't index all the numbers in the unit interval using natural numbers, so it's uncountable. And see your lecture notes for exactly why that's true. Okay, so I'm just going to draw this unit interval, and I'm going to take the event space to be something. Maybe I want to use all of the subsets of the unit interval, but I really can't. This is too large. Okay, so it really causes a lot of problems to use this event space. And if you, again, look at your lecture notes, there's an example which will kind of showcase why that happens. Okay, so this is again just something if you're interested in understanding the mathematical details, you can go and see that there. Okay, so a standard choice that gets us away from this problem is to pick a smaller event space, which is still infinite, but a smaller kind of infinity, and that's going to be the Borel sets. So what are Borel sets? They just consist of open intervals, let's say written as AB, and any sets that I can express using countable unions and complements of open intervals. Okay, and thinking about this, you can see that this immediately satisfies all of the rules I need for an event space because I have included some sets, and then I just said anything with countable unions and complements is already in there, so all of those properties are satisfied. Okay, how do I specify the probability measure for this example? I want every outcome, just in this particular example, to be equally likely. So I want the probability of getting any number in this unit interval to be equally likely. And what this forces me to do is to take the probability of every outcome to be 0. Okay? And this is strange. Why am I doing this? Well, otherwise, I would have the probability of the sample space being infinity by additivity, because all I would do is just take the infinite numbers I have between the unit interval and take their tiny positive probabilities and add them up. If I add up infinite positive things, I get infinity. So I can't make these outcomes have positive probability. They have to have 0 probability. Okay, so I'm not allowed to do this. I cannot assign probabilities directly to outcomes. And this is what we were talking about before, that it's a little dangerous to just think about probabilities as going to outcomes. They have to go to events. In this case, we're going to assign probabilities to the open intervals. Okay, so we're going to say that the probability of A to B is just B minus A. It's the length of the interval. Okay, so I've just drawn this up here. Probability of A to B is just B minus A, the length of the interval. And for any other event that I encounter, the way I would deal with it is just use the countable additivity property and the complement property to work out the probability. So let's just do an example. Let's say I want the probability of landing between a fourth and a third, or 9/10 and 1. Okay, so strictly speaking, this is not an open interval. It's a union of open intervals. So I'll use additivity to decompose it into the sum of the probabilities of 2 open intervals between a fourth and a third and 9/10 to 1. Okay, so this is additivity. And now I can use my probability measure to work out that the first interval has probability a third minus a fourth, and the second one has probability 1 minus 9/10. So that's a 12th plus a 10th, and that's 11 over 60. Okay, so the thing I want you to take away from this is that probability is not as simple as just assigning some values to individual outcomes and then just kind of summing up the probabilities that I see in my event and just going from there. I actually have to be quite careful. The good news is a lot of researchers have been thinking about these problems for a very long time and have built up frameworks, event spaces, probability measures that we can use in basically any context or problem or application we can think of. And we're going to rely on those frameworks as we go ahead. And this is just here to sort of remind you or point you to that fact that we're going to need a mathematical foundation in order to operate in these spaces. Okay, so we're not going to be asking you to construct your own event spaces like the Borel sets, but we just want you to appreciate that there's actually some subtlety going on here, and at times we need to be a little bit careful and maybe stick to the definitions a little bit more than you might in another class where you can kind of just go on intuition. Okay, so this is going to be the last time that we see continuous numbers, like let's say on the real line for a little while. We're going to set them aside and kind of deal with more discrete examples. And by the time we come back to real numbers, we'll be dealing with them in a framework that lets us kind of sweep all of this stuff about Borel sets under the rug and just deal with them in a much nicer framework. Okay, so we'll see that when we hit continuous random variables a bit later on. And for now, you can almost forget about this, except that we do want you to appreciate that there's some magic underneath the hood here that makes all of this stuff work together. Okay, that's it.